I would like to mention collaborators at various stages of the work of the project, and they are here listed in alphabetic order, just in case that I don't miss some of the names. A long list, and I would like to focus in this particular talk on the relation, because this is an operator theory conference, on the relation between operator theory and PDEs. This is quite well known, so does not need really to be advertised, but also connected to control theory and to show some sort of a synergism, like problems in control theory or ask for questions in operator theory, and solution comes exactly from there. Okay. No, now I cannot. Okay, so here perhaps I can move. So the motivation for this particular problem comes from quite applied field, and this is high frequency focus ultrasound, which is used in medical sciences, but there are also many others in engineering, mechanical engineering, and lithotripsy and welding, for instance. And the PDE models involve nonlinear acoustics. Okay, and there will be two types of equations. One is referred as Westerwald-Kuznetsov, and the second one more Gibson-Thomson equation. Okay, so the both equations are equation of nonlinear acoustic. However, the first one, Westerwald, is a second order in time and is characterized by infinite speed of propagation, and it's of parabolic type. Okay, while the MGT, which is more Gibson-Thomson, is a third order in time. And in fact, this was somehow constructed a long time ago in response to some criticism of infinite speed of propagation in acoustic medium. So what expectation is that acoustic waves should propagate with a finite, or heat wave with a finite speed. And that's what exactly introduces the third derivative in time in the abstract dynamics and creates a quite different model. So first question to address is a global well-posedness and nonlinear semigroup arising in this quasi-linear PDE models. Then a relation between a second and third order in a sense that is when the parameter, which is time relaxation, goes to zero, you would expect that there is some convergence of solution in appropriate sense. Okay, so that's kind of non-trivial. And eventually, I would like to talk about a boundary control problem. So if you want really to solve some of these problems arising in application, one needs to understand the structure of dynamics and what happens on the from the boundary. So what are the challenges? Challenges, first of all, this is a nonlinear acoustic of quasi-linear type, so it's a quite heavy nonlinearity. I would like in this talk to emphasize connection with so-called maximal regularity of operators of generators of semigroups, because it's a quite well-known topic, and particularly recently there have been some new developments and very much enters this area. And on the other hand, the hidden regularity for Dirichlet-Neumann hyperbolic maps, which are related to hyperbolic type of dynamics. Again, the maps which take you from the boundary to from the boundary to the normal derivative. One particular feature of these models are singular perturbation, because when parameter which distinguishes between two types goes to zero, then the dynamics become singular. Okay, so the transfer from hyperbolic to parabolic, it's a singular one. And boundary feedback control problems for this particular models is particularly singular. And as people who work in the control area, they know that feedback control is often constructed by use of some Riccati equation or Hamilton-Jacobi equation. So what is happening here, the coefficients are very heavily unbounded. So this is again an operator theory problem. So this talk will consist of three parts. Part one, I just review some of the facts of MGT dynamics. Second part, I would like to emphasize MGT from the boundary. So what happens really when the boundary data are non-smooth, because like in PD, everything has been known for a long time. What happens when boundary data are smooth, because you can homogenize and you can look at the problem from the right-hand side. But for non-smooth boundary data, we have measures and things are much more complicated. And third part, I will talk about application to optimal control and similar Riccati equation, algebraic Riccati equation. Some of the pictures, you see that here you have a magnifying glass and piece of paper, and there are some, say, rays, solar heat waves, which are concentrated and eventually make hole. Okay, so that's a typical situation when you have some medium, acoustic medium, and you have waves, okay, which are concentrated at one point. The concentration focal point is very important here. More important application is in medical sciences when you have a body inside like a kidney. I think this is a typical thing for kidney therapy, kidney stones, and you have some focus lesion given by a given point, and you apply control via some transducer which emanates rays exactly hitting this point. So that's a control problem, how to use a control outside the body in such a way to find, to act inside. Okay. No. Here the control problem, in fact, I'm going to consider the following configuration, that you have an acoustic medium, this is this blue part, and control is applied here on this semicircle, whatever, oval part. It's a via piezoceramic disc, and we apply here some electrical piezoceramic current, and we try to focus exactly in a given point. Okay, so this is the situation that we would like to describe. Now, modeling, I just say a few things because perhaps there's no point to talk too much about the modeling because these models are already established. But essentially, the model consists, it's a combination of three equations. Rho means density of mass. V is acoustic particle velocity. So the first equation is just mass concentration. The second equation is equation of momentum. So this is a famous Navier-Stokes equation. Capital T, it's a Cauchy-Poisson tensor, which has a Laplacian inside. And the last equation is entropy equation, which relates the temperature to the heat flux. So the variable in which we are going to consider equation is variable psi, which is it's essentially potential function corresponding to the velocity, or the pressure, which corresponds to the material derivative of the velocity. So this will be a scalar quantity. Okay. Important part here in derivation is to distinguish between so-called Fourier laws and Catania laws. When you try to model a relation between the temperature and heat flux, classical method relies on a Fourier law. So this is Q is the heat flux and theta is the temperature. This is the relation. But this, of course, is going to have infinite speed of propagation. Catania law allows for some small relaxation. Depending which law is you are going to apply, we end up with either Westerwald equation, which is second order in time, or Moore-Gibson, third order in time. You see that the nonlinearity here, I don't emphasize, are the same in both cases. However, in the case of MGT, we do have a third derivative in time of the pressure with a small parameter tau. I would like to give a credit to modeling aspects to Jordan Pedro, who works with Navy Labs, Ivan Christoph from Stanford, Brian Strogan. So these are people who have been involved for a long time. And personal thanks to Mauro Fabrizio, who also provided a lot of information from a mathematical physics point of view. Okay, so let me just look at the Westerwald equation, which is the second order. And nonlinear, if you rewrite this thing in a compact form, then you can see that nonlinearity enters as a degeneracy in front of a second derivative. So this term can be equal to 0 or even negative. And there is also on the right-hand side. This is just rewriting right-hand side. Okay? So one has to deal with this kind of a situation. So what is known? What is known? Since this is a quasi-linear equation, so when you expect that solution would exist for sufficiently small data, But the main issue is to show that the smallness will not depend on time. So in that sense, they are global. And this has been achieved in part with the paper with Kaltenbacher, and the energy which are considered, so we have here some norms, okay, are essentially two derivatives for time and two derivatives for space. So these are smooth solutions, and for the smooth, sufficiently small data, one can show that solution exists globally, and for any time t which does not depend on the values of initial data. That's important. And now why is that? Because behind there is an exponential decay of the linear dynamics. So that's very important, exponential. And that is known for linear dynamics is here so-called strongly damped wave equations of that result has been known. Okay? That there is exponential decay. So there is a way of taking advantage of it to get a globality of nonlinear solutions. So you also have a exponential decay of the solutions. Okay? Now, what is the idea of proof for this case? Main tool, okay, you have to exploit analyticity of the linear semigroup. Now, you find that this semigroup of generated by the second order damped wave equation, because damped because the fraction B is positive, that goes back to work by Chen and Fujani in 86. And that's very important because semigroup is analytic. And that helps very much in resolving by fixed point essentially suitably constructed. And also maximal parabolic regularity is very important here. And as you probably know, analyticity does not imply maximal parabolic regularity, but unless the space is a Hilbert space. Okay. And then exponential decay of linear dynamics allows to use so-called barriers method and nonlinear invariance in such a way that you can construct a fixed point. So this is a very brief description. So here perhaps I'll just mention a few words about maximal regularity because this is a tool that is very heavily used in this kind of problems. So what is maximal regularity for a given operator? You have a closed operator defined on some space X, define domain of A in X, and you consider abstract Cauchy problem, ut plus A of u equals to F with some initial data. And he says that A admits maximal regularity if and only if the map from the right-hand side and initial data into the solution is a topological isomorphism between the following spaces. You take a space LP with respect to time with a variation X. So the F is exactly in the space. And initial data in the space of the traces. What is space of the traces? This is real interpolation between X and domain of A, okay? With a factor P because the P is here. And you obtain solution exactly in the same, bounded in the same space. See? So there is an estimate which is very, very useful, describing the property of maximal regularity, and also analyticity gives you a nice control of the kernel in the convolution, which is singular at t equals 0. So that's also another ingredient which is very useful in the analysis. Okay. So the question is, if we go back to this Westerwald equation, we want to know what are the spaces, what is X, and so forth. For generation on analytic semigroup has a variety of spaces on which you can carry this kind of analysis. However, you have to have also a correct space for maximal regularity and also space where you can handle nonlinear. Because it's known that to handle nonlinearity, you have to have a certain amount of smoothness. And what is happening is that the space where we want to work is a space which is a product of a domain of the generator plus the basic space. Okay, so that is the one when has all the properties determined. Okay, and then if you write the second order equation as a first order equation on this particular space, then we can use maximal regularity theorem, and we know that there is an isomorphism from right-hand side in LP in the space X into LP in domain of A, so each term is well defined, and also derivative. Okay, and trace and solution is in a space 1 minus 1p, so that's a trace space. which is for Hilbert space would be like a domain of A1 half. You can think of it. So as a result of that, one obtains that you have a map from F and initial data to the solution towards the derivative. It's an isomorphism from the LP of LP, if I take X equal LP, to the Sobolev spaces of the order in initial data in 2P and 2 minus 2 over P over P. If P is equal to, then you get exactly 1. Into the same space, this isomorphism. And the fact that this isomorphism helps a lot in nonlinear analysis, and it's high enough. So one can have definitely local existence for small data, but owing to exponential stability and using so-called barrier method, one gets a global result. Okay? And these results were obtained almost 10 years ago. Kaltenbach and myself, Meyer and Wilke have a paper also on using LP spaces as the model. Now let's go to the third order equation. So what we have, we just add tau, which stands in front of a third derivative. Okay? So replacing Fourier law by Maxwell-Catania law, it's exactly changing here the picture. Okay? B is a coefficient of diffusivity, and one has to say up front that if B is equal to 0, the third order linear equation is imposed. This is a result due to factoring. So it's a bit different when you go from second order equation to the third order equation. So B has to be strictly positive. And this is the equation that you understand. Okay? And here there's a statement that I'm just quoting from one of the physics papers, that the presence of the third time derivative is typical in so-called extended irreversible thermodynamics. And this is a story which somehow tries to rectify the issue of a propagation of the heat waves with infinite velocity, with infinite speed. Okay, so by introducing this third derivative, we have a finite speed of propagation. Okay? So when this tau is equal to 0, we have a parabolic-like problem. When tau is positive, it's a hyperbolic. Okay, why it is hyperbolic? There are various ways of proving this thing, but let's look at the spectrum. Okay, the spectrum consists of 3 branches. Okay, where 2 of them are symmetric and they approach vertical lines, like in hyperbolic, and 1 branch is you have eigenvalues accumulating towards a point of continuous spectrum. So in SO, you have definitely hyperbolic behavior. So here's just concrete examples, and you see that the branches are going, depending on diffusivity, they go vertically toward lines which have a positive imaginary fact, and there is a point of continuous spectrum. Okay? So this is a previous example. Perhaps you can see that if parameters are not well balanced, it is possible that this problem is unstable completely. And in fact, dynamics can be taught, and that has been shown as well. Okay, okay, and here's another situation when you have, you see in parabolic problem, you will have this branch going somehow in a contained triangular sector. Here instead goes to vertical line. Okay, so that's a difference between the two. So in abstract population, for tau equals 0, we have equations. So A, think of it as an operator that then you can take a Hilbert space self-adjoint, because we'll be talking about Laplacian, and we have the second derivative with possible degeneracy. For MGT, degeneracy appears in front of a second derivative, okay? And tau is okay? So here I've just written these models for zero boundary conditions. So these are 2 models. Okay? Now, what is known about various cases? K represents nonlinearity. So let's look at the linear problem. So we know that when tau is equal to 0, the semigroup is exponentially stable for any alpha positive. So when tau is positive, the stability region is only for the coefficient alpha minus tau c square over b being positive. So you have a sum cutoff, and you cannot have a you can, even for positive alpha, you might have unstable. So that's exactly what was illustrated. When tau equals 0, the solution exists globally, provided initial data are small with respect to topology. This is domain of A is H2, and this will be H1. or some Sobolev spaces above the 2 and 1. For tau greater positive and gamma positive, so it means that alpha, the dissipation has to be strong enough with respect to the relaxation parameter. Of course, diffusivity helps, okay? But speed of sound does not. So you have on another space. So this is right now completely understood how to construct solution to these equations. Okay? So parameter of stability is exactly this alpha minus tau c square over b, and the energy function, which corresponds to MGT equation, are exactly here. You have a1 half will be h1 for a classical application, h1 and 2, but also you have to have here higher for nonlinear problems. So these are like secondary. Okay, and owing to exponential stability, one can show global solution. Now, if you have a critical case, so this gamma is equal 0, or perhaps is equal 0 at some points only, then you have an issue of stabilizing. You have to introduce some sort of a damping, which would provide exponential decays. And there are two ways of doing. One is a memory damping, and that is introducing some integral here. Obviously, I will not talk about this. There is a work by Filippo Deloro, Vittorino Prata. We also have joint paper with Sonny Van. I rather concentrate on a boundary damping on a part of the boundary, which is work with Notchlo, Bogarty, and Roberto, which is exactly in line with the application that we want to study. Okay? But if it's critical case or almost critical case, you need to stabilize dynamics first. Here I will note, there is also analysis of asymptotic analysis, what happens when tau goes to 0, and the bottom line is that eventually solution converge strongly, and it was an open problem because weak convergence was established in the last year, and was not clear that one can go from weak to strong. This was just a mathematical issue, and numerics indicated that it should be strong convergence, and then recently we were able to resolve this issue. So it means that oscillations can be removed. The reason is that the operator is here singular. You have a tau, it goes to 0, so you see what's happening when you try to use any sort of a Trotter cut or other problem. It is not really appropriate. So we have all the estimates. I will skip this part. Okay? So now I would like to go to part 2. What happens when you put a non-homogeneous boundary condition? Okay? So what happens with the solution? So we have a semi-group. Yeah? I'm looking right now at a linear problem and with 0 boundary condition. And one question of interest is, okay, if you have an initial condition given in the space at which you have a generation, if you see it's like a hyperbolic because a scaling is by one derivative, h2, h1, h2. So this is second derivative, first derivative, and solution. And then you ask a question, what happens with the normal derivative? More generally, you can put boundary data on the boundary and then still look for the normal derivative. Okay, so first you want to see what sort of a brutal approach, what kind of result will give you. So brutal force interior regularity plus trace theorem will tell you that if we start with the solution in a space h2, h1, and 2, so it means the solution has two derivatives. So normal of u, it's a gradient restricted to the boundary. So gradient will have one derivative. And if restricted to the boundary, this will be 1/2. Okay, question is it really the best you can get? Hidden regularity is referred to the property, in fact, was introduced by J.B. Lyons. This regularity that does not follow from interior regularity and trace theorem. This is unlike parabolic analytic estimates, which typically on the boundary you obtain from the regularity. So I would like to present some result on wave equation because this is kind of a toolbox in some sense. So what happens there? Because hidden regularity was introduced in the context of wave equation. So if you start with a wave equation and you take initial data, okay, and take 0 boundary data, then you have the same question. What happens with a normal derivative if data are in H1, L2, and the right-hand side is L1, L2, then solution is going to be H1, L2. That's a semigroup result. Okay? But then normal derivative, according to this numerology, will have minus 1/2 derivative. Okay? Because take a gradient and apply formally trace theorem, so you lose 1/2 derivative. However, hidden regularity tells you that no, this is not the best you can do because you can improve this 1/2 and you get Fourier too. And that's what is hidden because does not follow from optimal results in semigroups. And interior regularity is optimal. We are not losing anything. But on the boundary, on taking essentially restriction to the boundary, we can do better. And this result is here. The joint work was done in 86 long time ago. And as you see, there's all bunch of results of the same nature, starting with a different initial data, different boundary condition. Bottom line is that this gain of 1/2 derivative in each case for the radar equation. Now, we say, in fact, we also label this property as hidden regularity. However, it is not that hidden if you look at right way, say, from the point of view of Fourier analysis. And this is, I worked with Roberto several years earlier, when what you do, you just take a half space and you do Fourier analysis and you transform equation in such a way that you solve an ODE in a normal direction and tangential, which means tangential, geometrical, and time, you send to Fourier transform. Okay? And then you get so-called Dirichlet-Neumann map. So you feed it on the boundary function G with a Fourier transform, and then you have a normal derivative. And then you can see that exactly this operator here, it's operator of the first order, it's the square root of the Fourier transform second order. So therefore, Dirichlet-Neumann map uses only one derivative, not 3/2 derivative, because 3/2 would imply if you just follow the trace term. Of course, this is kind of a very special situation when you can do this subspace and so forth. However, was already indication. One thing to note is that if you look at the Neumann problem, situation is different. So if a map, hyperbolic map, Neumann to Dirichlet, does not have such a nice regularity simply because you have here you have to divide by the operator, which has a singular, which has a certain compensation in characteristic in hyperbolic sector. So this is a Fourier analysis. So there is some gain hidden, but not as good as in a previous case. So just to conclude, in general, when we have a geometry, the commutators is pretty messy, but the optimal result, which is known now, is that if you take a D'Alembertian with a normal derivative G in L2 and zero initial data, your solution in the interior has 2/3 derivatives. Expectation could be that should be one derivative. Expectation based on the Dirichlet-Neumann map, but that was proved by Rausch given in 78 that that is not possible unless dimension is equal to 1, okay, of the domain. And that result is optimal due to Tatarov proved that it's optimal. So there is from the normal boundary condition to the interior, we gain 2/3 derivatives. So we do not obtain finite energy solution. So the final conclusion is that Dirichlet-Neumann hyperbolic map exhibits more hidden regularity than the Neumann-Dirichlet hyperbolic map. So we should be aware of it. There are several methods to exhibit hidden regularity, so we know how to proceed. Zero differential calculus, there are multipliers applied to smooth solution and some limit transfers, duality transposition, semigroup methods, and analysis of sine of a sine and cosine operator, and also via first order hyperbolic system. Dirichlet-Neumann map, if you feed Dirichlet data, the basic principle is that if you have H1 Dirichlet data, you obtain H1 solution. So this is against gravity in some sense because you don't lose any regularity because of trace term. More generally, HS Dirichlet boundary data imply HS solution. Now let's look at the MGT. So we are looking at the third order equation and we try to do a similar thing. So first of all, we can see that the operator, this is right now 3 by 3 matrix operator, can be written as a some principal part plus perturbation of lower order. So for the regularity purpose, it's just enough to look at the principal part. If you do this, the problem is trivially simple, looks trivially simple. So you have a third order derivative equals Laplacian of the first derivative, and on the boundary is equal G, and for simplicity, everything, all initial data 0. So what would be the favorite method to use? Of course, substitute WT for the new variable equal to Z and solve wave equation with a boundary data, which is time derivative of the Z, and analyze what can we say. Do we get the results as expected? And now here it's a big surprise, because if you take G identically 1, which is infinity, very nice, very smooth function, then we have, of course, derivative equal to 0, and we get a solution equal to 0. So obviously there is something wrong, and this does not correspond to the original problem, which is supposed to have a 1 on the bound. And in fact, what is going on, the correct solution in, say, in one-dimensional problem is that W itself will be characteristic of x minus t, so there you have a characteristic line, and time derivative is a delta function. The delta function is not equal to 0. Okay? So this brings the issue that we have to have a correct model for the solution. Okay? So for wave equation was a transposition method or semigroup method for that matter. That's what seems to be implying much more. Okay, I will skip this because I'm not going to say much. So what is the correct method? It's we want to consider third order equation with rough boundary. It can be shown that for the simplified model, the solution can be written as a variation with 0 initial data, as a variation of parameter formula with a sign operator, and A is a generator of the semigroup corresponding to Laplacian, and with a Dirichlet extension, harmonic extension from the boundary condition. This is the method that was in fact used for the wave equation our joint work with Young. And the derivative has a cosine. Okay? And that is a correct model, and you can check that there is this contradiction, okay, with delta function doesn't work, and key observation, the time derivative of the Laplacian is not the same as Laplacian time derivative, unless there is some compatibility. That was the issue with the previous model. Cosine operator is as always defined, second derivative equal A of C, and sine is in, and this is a harmonic extension. So by doing this, for general model formula is more complicated, but I think that the main also we have a lot of singular integrals, but the main idea can be conveyed on this simple case, because this can be also written in terms of the sine and cosine. So what is the result? The result is exactly as we would like to have, to exploit hidden regularity, which in fact does take place for the third order equation. And one can show that solution to MGT, okay, if you start with the boundary data in L2, has a solution also in L2, like for the wave equation. Okay? And then normal derivative is in H negative 1, which is also like for the wave equation. So the result is exactly as expected, and that's the result was by Roberto, or later we have a joint work with also Bogarty. Mucci Pandolfi have a paper on related problem, but they use a Volterra equation, some substitution for this the reduced Volterra equation, which in some cases is equivalent to this problem. Now, what is important that we really characterize solutions with the sine and cosine operator, okay? Because we have a lot of information what happens, okay, with the singularity. I want to convince you that these are really singular integrals that we cannot integrate normally, okay, regularly. Because if you take this combination, okay, we can take always A outside because this is symbolic operator. But if you look at this combination, so what do we have? This is a Dirichlet extension, so we know from elliptic theory has gains 1/2 derivative. G is in L2. So we have D applied to G in H1/2. Sine operator brings 1 derivative, okay, so it gives you +1, so it will be 3/2. However, A itself is a second order operator, takes out 2. So here we are going to get minus 1/2. Okay? And it's not what the result says. It's supposed to be negative. So there is a hidden regularity of of 1/2 derivative, which is really buried in the analysis of a sine and cosine operator related to this operator. Okay? And that's a way to have a good formulation of the solution plus properties of the sine cosine operator. Now I would like to finish with the third part, which is a control problem. And we have here MDT, and we consider non-boundary condition forced by some function G, like, you know, we want to focus on the tumor or to find some other things. And also we have observing boundary condition on the remaining part of the band. Okay? And that also should include the case of critical case when the parameter, stability parameter might be equal to 0. Okay? So this is a problem. The first result for this boundary control problem were obtained by people in Germany, Kaltenbach and Clayson, and it was motivated by very specific application. And what was happening was essentially calculus of variation when they were trying to hit this predetermined outcome in a space L2 with the controls which are classified by the space capital G, and these were very smooth controls. So you see that space G, it has a lot of derivatives, not L2. In control theory, we really want to have a control thing. We can think of functions which are 0, 1. Okay, so there is no differentiation. For the smooth control, where the maximum principle could be derived optimality condition and so forth. These results are reported also in Nobel Wolfgang seminars volume in 2018, when it's a paper of Kaltenbach. Okay? By using calculus of variation, but the problem is the same. So what we are trying to do, we are trying to precisely reduce regularity of control to the space L2. That's the main thing, and that's why the question of regular solutions was important before. Okay? So how do we model? And of course, we have to deal with stability, and there is a result on stability that with this observing boundary condition, one does obtain exponentially, it is possible to get stabilizable dynamics. Okay, and that's what we know it's needed to get a feedback control. Okay, so I'm not going subject to some geometric conditions. Okay? And one can write input-output dynamics with a lot of operators, some control operators, like as you see here, are heavily unbounded because A is Laplacian. This is Neumann map, which has only three-half of derivatives and so forth. So I will not go into these details, but just to give you an idea that transient dynamics is very rough. For the case when tau was positive, and hyperbolic and finite time horizon. I had a paper with Francesca Bucci in 2019 when we could resolve this problem on a finite horizon, okay, to get optimal control. However, now probably the best result is having information on stabilizability of the dynamics. For data which can be very, very rough, we do have unique optimal control with a target which is in a given space where you want it. The target is defining some L2 Lebesgue space. Transient dynamics is rough, but the target is well defined. And we have a solution to a self-adjoint positive operator, so-called Riccati operator, with a nice regularity property. Now, why is this nice? In parabolic dynamics, you know that this is due to smoothing effect of parabolicity. Here is due to the observation, which also had a smoothing effect. However, the Riccati equation is non-standard because the left-hand side is a classical linear. However, nonlinear part would be standard without the red term. Okay? So, and these are nonlinear terms. And we obtain optimal control in a feedback form through these operators, and operator G needs to be shown invertible, which doesn't have a symmetry that could guarantee, but this can be shown by contradiction argument. So this is the result of optimal control on L2 and because of the good regularity. So conclusion, we solve original problem with L2 rough controls. The observed quantities are in the Lebesgue space, but rough transient dynamics. Existence of solution to non-standardized equation was established, and feedback synthesis, which means online control action. Okay. Problems, okay, apply this paradigm to the nonlinear dynamics, because this is defined for the linear dynamics applied to nonlinear, and try to show that also nonlinear dynamics you can provide control. And also extension of the theory to more general observation operator. Here we just look at this particular application from Germany, from one branch of literature, where the observation did have some specific effect. Okay. Now, I have a lot of references related to various modeling and other aspects of the equation, so which probably will be available to everybody. I want to there is also paper by Stokes, because it's amazing. This Professor Stokes was looking at the equation of the effect of the dynamics in a very simple case. I should have this thing somewhere. Some escape from my list. Okay. Pedro Jordan is a person who knows a lot about modeling and also have a lot of interaction. And also Brian Strogan. They provide a lot of physics to the derivation and to the result and to the interpretation. Okay? What is possible, what is not. So I would like to thank for your attention, and my apologies for starting later.
Well, so then let us thank our speaker. So thank you so much for a wonderful talk. Let's see if there are any questions in the room or online. So if you have any questions online, please just unmute and ask the question. I see that Professor Trigiani unmuted, therefore he has a question.
No, I will never ask. I'm not going to jeopardize 41 years.
I see, okay. So any questions from the room, please? Okay. So far there are no questions, therefore let's thank our speaker. Thank you very much.